Okay, Geometry, Chapter 7, Section 5. This is actually the last section that we're going to be doing here in Chapter 7. So as we're getting ready for our Chapter 7 test, hopefully we see how this ties together a lot of the things that we've been talking about earlier in this chapter. Now, in 7.3, which we just got done with earlier, we talked about similar triangles and proving triangles congruent by angle-angle similarity, side-angle-side similarity, and side-side-side similarity. This section right here, 7.5, really just builds on a lot of those ideas because in every one of the problems that we're going to be looking at here, we are dealing with similar triangles. This just allows us to skip some of the formality of proving them similar and allows us to just go through things a little bit quicker. So we have three theorems to talk about today. The first one here is theorem 7.4, and I like the name of this one, guys. It's called the side splitter theorem. So it applies when you have a setup that looks like this. And if you take a look at what I'll call the original outer triangle, which is triangle ABC, so we have this triangle right here, and this would apply to any triangle at all that exists. And now what we're going to do is draw another line segment within that triangle that runs parallel to one of the three sides. So M and N are kind of just random points right there chosen on AB and AC. And if we draw it carefully so that line segment MN is parallel to BC, which of course is made obvious there or indicated by these red arrows right here, indicating that those lines are parallel. What this actually does is it creates two similar triangles, and we talked about this a little bit in 7.3. You've got triangle AMN right here, and then the big yellow triangle, which is ABC. And because we have parallel lines cut by a transversal, you have congruent corresponding angles here and here, and right there is the angle-angle similarity that we need in order to state that those two triangles are congruent. But that is not what we're here to talk about today, so I'm going to get rid of a lot of that junk I just put on that diagram right here, and let's talk about this quick, simple idea here. The side splitter theorem says that in addition to the full sides of the triangles being proportional, these little pieces right here, line segment MB and line segment NC, which are not complete parts of a triangle, can also be used within a proportion when we're dealing with corresponding sides. So it says that this top segment right over here, AM, can get divided by MB down on the bottom. So there's your AM divided by MB, and that ratio, the ratio of AM to MB, is identical to the ratio of AN to NC. So these two big sides of the triangle, AB and AC, get split by M and N, and that's where the phrase side splitter comes in. Some people like to look at this a slightly different way because they can get confused sometimes by the geometric notation. So if we just said, for example, that our side lengths here were W and X, and then this little piece down here was a Y and a Z, you could kind of do the same thing. Top left over bottom left, so that would be W over Y, is equal to top right over bottom right, and that would be X over Z. These two equations here really say the exact same thing, but on the left-hand side in black there, we use geometric notation for the measurements of our segments, and in red here, we're just using variables for the side lengths. So that's the side splitter theorem. Now, the thing about the side splitter theorem is most people understand it pretty well, but they tend to over-apply it in places where it does not belong. So let's take a look at an example here. We have one large triangle that goes, I didn't label any points here, but a large triangle that goes between these three vertices here. And then we have this extra little segment drawn in the middle parallel to one of the sides. So the two sides of the triangle that are being split are this top piece up here, I'll highlight that in yellow, and then this bottom piece right down here. And the side splitter theorem says that as long as that line segment in the middle is parallel to this one over here on the left, they will be split proportionally. Okay, so the numbers we're going to be looking at here are the X and the 12 on the top side, and the 2 and the 8 down here on the bottom. Now the cool thing about the side splitter theorem, guys, it sets up exactly the way that it looks. It's already in the right order. If you take a look at those four numbers that I circled, X is in the top left corner, so I can put an X right here. 2 is in the bottom left corner, so I can put the 2 down there under the x. 12 is in the top right, so that can go top right. 8 is bottom right, so that can go there. Now, you can set this up a lot of different ways. More the way that we did it on that theorem would have been something like 12 over x is equal to 8 over 2. That would work as well. In problems like this, let me see if I've got this right, you always have 8 different ways of setting up a proportion correctly. So just because my way might not look like yours doesn't mean you're not going to get the right answer. Let me show you what I mean. If I go back to this way here and we cross multiply the x times the 8, that's going to get us an 8x. The 12 times 2 will be 24, and we'll divide both sides by 8 here, and we're going to get x is equal to 3. So that's the answer we got setting it up that way. If we had used this other method, well, when we cross multiply, this is going to look familiar. 8 times x is still going to be 8x, 12 times 2 is still going to be 24, and dividing by 8, we're still going to get x equals 3. So any way you want to do that, like I said, there's 8 different ways of setting up these proportions correctly. Now, this is what I wanted to warn you guys about here just a little bit. All right, the side splitter theorem works, obviously, on the two sides that are being split. The problem here is that the y that we're dealing with is one complete side of the original triangle, and you'll notice that that side is not being split by this little parallel piece here in the middle. So when you're dealing with one of the two parallel sides, what I really strongly advise is that you guys take just a minute to redraw the larger outer triangle and the smaller inner triangle, but to draw them separately. Now, those two triangles are going to be similar to each other. And if we can take the time to show this, I think we're going to understand the relationship. If we don't, people tend to make mistakes on this a lot. Okay, on the big outer triangle, which I have here on the left, I'll call that triangle number 1, we know that the left side of that big triangle here is y. And if we take a look at the bottom, we have a 2 and an 8 that we would have to add together to get a 10 here for the length of the bottom side of the big outer triangle. In triangle number 2 here, this smaller one, the left side, which is this piece right here, has a length of 6, and the bottom side, which goes from here to here, well, that has a length of 8. And once you set up the problem like this, it looks just like a problem that we did in 7.3, and here we go. The y on the left would correspond with the 6 on the right. The 10 on the left corresponds to the 8 on the bottom. We would cross multiply now to get an 8y is equal to 60, and we would divide both sides by 8, and we're going to get y is equal to, and I do believe that's going to be a 7.5. All right, so that's the way to handle that problem. And like I said, it's one that people tend to get wrong a lot. The one thing I want to warn you here, guys, I want to take just a second and show you a little error analysis. A lot of people tend to over-apply the side splitter theorem, and they tend to set up something like this, that y over 6. Okay, they're looking here, and then they want to look usually here and here. And they get something like y over 6 is equal to 2 over 8. Now, if we follow that through, we're going to get an 8y equals 12, and dividing by 8, we're going to get y equals 1.5. And I want you guys to stop and think about whether or not it looks realistic that this side over here could have a length of 1.5, especially considering that that side right there has a length of 6. It doesn't make any sense. Y definitely needs to be bigger than 6, and that's what we came up with right here. So you want to be careful about over-applying the side splitter theorem and using it in places where it's not relevant. Okay, the second, I lied, this isn't actually a theorem, but this is a corollary, and if you missed this during the year, a corollary is like a theorem. It just kind of tags along to another existing theorem. And this corollary says that if you have 3 parallel lines intersected by 2 transversals, and that's what's going on in this diagram. We've got line AX on the top, BY in the middle, and CZ on the bottom. Those 3 red arrows tell you that those lines are all parallel. And then we have transversals, 2 of them intersecting them both. Line AC is one transversal, and line XZ is a second transversal. Okay, and this corollary says that if you have this set up, 3 parallel lines and 2 transversals, then the segments intercepted on the transversals are proportional. That doesn't make a whole lot of sense, but when we look at the diagram, people usually figure it out. The ratio of AB right here compared to BC. So if AB to BC is equal to the ratio of XY over here on the right to YZ underneath it. Okay, I guess we could thicken the plot just a little bit right here. You could actually say that same ratio exists for the entire segment that goes from A to C. Actually, that kind of would have come in a different spot. Anyway, I'm sorry, that same ratio, let me write this down here. That ratio of AC on the left compared to XZ on the right would be the same as the ratio from the top sides, AB on the top left compared to XY on the top right, and that would be equal to also then to the bottom left to the bottom right ratio of BC compared to YZ. So all of those 3 ratios right there are equal to each other. But that's kind of the simplistic version of what we need there for this corollary to the side splitter theorem. So let's take a look at what's going on with this. And this is another one that we can sometimes overthink a little bit. The nice thing about it is that when it applies, and it does, we have 1, 2, 3 parallel lines cut by 2 transversals. We now have all these pieces here, a 10 and a 3 and a 12 and an X. Guys, this proportion sets up exactly the way it presents in the problem. If I read this thing, the left side is 10 on top and 3 on bottom. So 10 over 3 is equal to, and now the right side gives me a 12 on top and an X on bottom. That's it. All right, cross multiplying, 10 times x is going to give us 10x, 3 times 12 is going to be 36, and we'll divide both sides by 10 quickly here and get x is equal to 3.6. I'd love for you guys to get in the habit of looking at this and deciding if that answer seems realistic. If I compare the 10 and the 12, 12 is just a little bit bigger than 10. So if I thought this was a 3, and I'm guessing now this is a 3.6 on the right, that seems pretty realistic to me. So that's the correct answer here, for example, 2A. All right, and the second theorem, really the third big idea we have to talk about today, is theorem 7.5, and it's called the triangle angle bisector theorem. This one isn't as obvious that it uses similar triangles. If we wanted to actually prove this theorem, we could walk through it, but in my experience, nobody really cares why it works. If that bothers you and you'd love to see an explanation, let me know. I'll be happy to work through the proof for you. But here's what it says. When you have any triangle, so in this case we're going to focus on the triangle in blue, which is triangle ABC, and when one of the angles is bisected within that triangle, and that's what this red ray is doing. Ray BM bisected angle ABC to create 2 smaller congruent angles right there. What that does is it splits the third side of this triangle, which is AC, and it does so in a manner that's proportional with the 2 sides in the triangle that were not split. So there's a lot of different ways to write this, but here we go. The ratio here from A to B, so we'll go AB here, which is this side of the triangle, compared to the other side of the triangle down here, which is BC. So the ratio of AB to BC is equal now to the ratio of AM to MC. AM over MC. All right, so it's like this left side over the bottom side is equal to kind of the left side over the bottom side of AC, which got split by that triangle angle bisector. That's one you kind of just have to practice to get the hang of there, guys. All right, let's see that in action here. So what do we have here? We have a blue triangle and a red ray coming out of one of the vertices of that triangle, and it is bisecting the angle it was drawn from. The double tick marks indicate that those 2 angles are congruent, which makes this red ray an angle bisector. And that means that we've got a proportional relationship between the 2 sides of the original triangle that didn't get split and then the 2 pieces of the third side that did. Okay, and this is another one that in a nice case like this, it sets up just the way you were going to write it. 12 is on the top left, 9 is on the bottom left. So this is going to be a 12 over 9. This over this is equal to a 20 over x. Sometimes we make these harder than we need to. All right, the 12 times the x is going to give us 12x. 9 times 20 is going to be 180. We're going to divide both sides here by 12, and we're going to get x is equal to 15. Now again, before you box that up, ask yourself if that seems realistic. If we compare the numbers on the left, 12 and 9, to the numbers on the right, 20 and x, all the longer sides are on the right side of this figure. 20 is longer than 12, and that tells me that x should be bigger than 9, and it looks like that's what we have. Also, if we compare it vertically, if we look at these two numbers, 12 is longer than 9. That tells us that this 20 should be longer than the x is, and that appears to have happened here as well. So that's our answer right there, guys. X equals 15, and that makes some sense, I think. And I wanted to do one more with you guys. This is another angle bisector theorem, but it's presented just a little bit differently, and you will see some problems like this showing up on your homework from here to there. So this would have been perfect, everybody, just like the last problem, if the 21 was given to you right there. Don't write this down. But in this case, it just would have been 8 over 21 is equal to 6 over y, and we would have gone on our merry way, and everybody would have been happy. The problem is that the 21 doesn't just represent this distance from here to here. All right, this one's actually a lot more complicated than that. The 21 represents the entire bottom side. So we don't know how to do this unless we have some representation for the length of this line segment right here. Well, this is something that hopefully we're going to pick up by the end of the summer if we don't already have it down. If the entire bottom side has a length of 21, whatever the length of this piece is right here, you would subtract that from 21, and that would get you the length of this. So, case in point, I'll fix this in a second, but if I had told you that this piece right here had a length of 10 and the entire bottom was 21, 21 minus that 10 would get you 11 for the length of that side. Or maybe if they had told you this was equal to something like 7, well, if the whole bottom side was 21 and this right piece was 7, 21 minus 7 would give us a 14 right there. The 14 and the 7 have to add up to that 21. Now, people can usually understand that when it comes down to something concrete like actual numbers. But when we're given variables, that tends to bother people a little bit. But luckily, it's really the exact same concept. What we do is we take the entire piece length, which is 21, and subtract the piece that we know, which generically is y. And this is actually easier because there's nothing we can do to simplify this expression. You take the total of 21 minus the piece on the right, which is y, and that is all you can do to represent the length of that bottom left side. So now we have the 8 and the 21 minus y on the left side, the 6 and the y on the right side. So again, we have a proportional relationship, and it sets up just the way it's presented. Top left is 8, bottom left is 21 minus y. Top right is 6, bottom right is y. So that's the proportion we now have to solve. The 8 times the y right here is going to give us an 8y. We've got to multiply 6 times the binomial of 21 minus y. So I think in every section of notes we've taken in this chapter, we've had this case of monomial times binomial, and we've got to use parentheses in order to do that. Okay, we're going to distribute the 6 in there, and we're going to get an 8y is equal to, that is 126 minus a 6y. We want to move the smaller y term to the bigger one. So we're going to move a negative 6y by adding 6y on both sides. And what's that going to do for us? Now we're going to get a 14y is equal to 126. And if I had a little more room, I would divide both sides by 14, and we would end up with y is equal to 9. Okay, what that would mean, let's take just a second and see if we can get this to work out. If y was 9 and this entire bottom side was 21, 21 minus 9 would be 12. Comparing the 8 to the 6, 8 is longer than 6, 12 is longer than 9. Looking this way, 8 is less than 12, 6 is less than 9. That answer there makes a lot of sense. So we're going to box that up and feel pretty good about our answer of y equals 9. All right, guys, that is all the notes we have for 7.5, so let's give that homework assignment a try. Let me know if you guys have any questions, and good luck.